Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is a lecture on building and using linear models for intermediate algebra. This is really everything in intermediate algebra, at least the first part of it, builds up to this point. What we're going to do is take all of our knowledge on equations of lines, slope, understanding the meaning of slope, all this stuff, and we're going to put that into action with actual applications. And all I'm going to do here is maybe one, possibly two applications, but in these two applications we're going to do a lot, and I mean a lot, of interpretation. And we're also going to use a graphing calculator for those who have graphing calculators, although definitely this is a graphing calculator is not necessary to be able to do the stuff that I'm going to be doing here. In fact, most of the stuff I'll do without, but still every once in a while I like to sneak a graphing calculator in. Pretty much the entire example set that I'll be using is going to focus around this example. The percentages of Americans who sent out their tax returns to the IRS electronically are shown in the following table. And here we have in the first column, this column represents years: 1998, 2000, 2002, 2004, 2006. And then the rightmost column is the percent of Americans in that year who filed their tax returns to the IRS electronically. Now part A, and there's going to be several parts here, we're going to let P be the percentage of Americans who sent out their tax returns to the IRS electronically T years since 1995, and we're going to create a scattergram of this data. So now that I've said the word, I should probably define it. And my definition is going to be both for scattergram, scatter plot. They basically mean the same thing. They're used interchangeably, those words. All it is a graph containing all the data points in a given set of data. Now, before we can actually plot this data, we have to pay attention to a couple things that were mentioned here. P is the percentage of Americans who sent their tax returns to the IRS electronically, but T years since 1995. So T is the number of years since 1995. So we need to kind of adjust our table here, or maybe we should create a new table just like this, T and then P, where T is the number of years since 1995. For example, 1998 here corresponds to 3 years since 1995, and in that year 19% of Americans filed tax returns electronically. The year 2000 is 5 years since 1995, and 2002 is 7, and so on and so forth. So let me go ahead and just jot these down here. And what we really want to do is want to pay attention, because a lot of real world examples do this, where they change the input variable slightly. Instead of saying, we're going to let T equal 1998 and then 2000 and 2002, it's much easier to deal with smaller input values. So we're just saying, since T is the number of years since 1995, now our input values for this data are small, they're manageable. So when we plot it, we don't have to go over 1,998 units. We only go over 3 units. So let's go ahead and plot this data. So all I've done is move the table over to a new window, and I'm just creating a set of axes here. I know my input values are T's, and that stands for number of years since 1995. And I know my output values, which are P, is percent US filing electronically. Maybe that's just an easy way to say it. All right. So now that we have that information there, we can go ahead and plot some data points. Now, because I'm plotting this freehand, it's not going to be the best in the world. One thing you have to notice is that our input variables, our T variables, the ones that go along the horizontal axis here, go from 3 all the way up to 11. So the scale I'm going to choose, I'm just going to go by ones here. And the scale for the vertical axis, which is our P axis. Well, we have numbers like 19 all the way to 55, so going by values of 10 might be a good idea. And there's a couple ways. Some people might break this axis and start where 19 is very low down. I'm not going to do that. I'll go ahead and just say that this is 10, that's 20, there's 30, 40, 50, 60, 70, and so on and so forth. So it's 30, 40, 50. All right. Now let's start plotting some values here. When the input's 3, the output's 19, so that looks to be probably right about there. When the input's 5, the output's 27, and of course I can keep going through. I'll just pause this while I plot these out. So we're actually pretty much done with the very first part of this, which is just creating a scatter plot. Now let me just show you how to do this using a graphing calculator if you have one. Now if you do not have one, a graphing calculator, then you can go ahead and advance this video until you see the graphing calculator disappear. But for now I'm actually going to go ahead and show you how to use one. I'm just using a TI-83, but they all kind of operate the same, the 83, the 84s, the 82s. They all have the same button pushes that we're going to do. And whenever you want to create a table of data that you're going to plot, you have to go via the stat menu. You're just entering, in computer language, you're entering in a bunch of statistics here. So I'll click the stat button, and you have all these little menus here. You can navigate these menus by hitting the right arrow to go to these other sub-menus, or you can hit the up and down arrows to go down these menus. We're actually going to edit a list here, so I'm going to hit enter to edit, and you'll see I have a list 1, a list 2, a list 3, but there's nothing in those lists. This is like my x values, this is like my y values, or in other words, my t values and my p values. So I'll just enter the values here that we have for t, which are 3 and 5, 7, 9, and 11. Okay, and then you can use the right arrow to get over the next list and enter these values: 19 and 27, 36, 45, and 55. Now once you've done that, I would highly recommend to click second and then quit. Generally just to get back to the home screen, that's always a good idea. Now I really want to make a graph of this data, so if you remember all the graphing menu items, this group of top keys up here. So if you hit the y equals button, you'll notice there's nothing in here. You might have an equation error. If you do, clear it out. But what I want to do is I want to actually plot the statistics, and if you look right here where my cursor is highlighted, there's a word that says stat plot, and it's accessed by using the yellow key, the second key. So access that stat plot menu, and now you see, oh, when I did that, it brings up a sub menu, plot 1, plot 2, plot 3. They're all off right now. What I'm going to do is hit enter to turn on plot 1. So I'm just going to highlight the word on and hit enter to select it. So now it's on. These are the type of plots that it can do. I could tell you about all of these, but the fact is you only want the first one to be highlighted, so that's fine. And then it says, what does your X list come from? Well, it's from list 1, and my Y list is from list 2, right? X list is list 1, Y list is list 2. If yours doesn't say L1 or L2 there, you'll see right above the number 1 is a yellow L1. So you could hit second, the number 1 would put L1 there. And then the mark is just what kind of dot do you want on there. Now if you just hit graph, hardly anything's going to happen. In fact, you don't really see anything because all this data is off your screen. This screen is going from x equals -10 to y equals +10, and x and y equals -10 to y equals +10. So it's better to zoom. So hit zoom, and you can actually zoom right into the statistics. Just scroll on down here, and one of the further options down below is zoom stat. That means it'll zoom in to fit all the data into your window. And there it is. And look how similar these two are. We did pretty good at doing this. So far so good. This is how you make a scatter plot on a graphing calculator. Now, Everybody who did not want to view the graphing calculator part, you can come back. Let's go ahead and move on. In part B, we're being asked to draw a line that comes close to the points in our scattergram. So let me go back here, and you'll see here's the points in the scattergram. All I need to do is possibly grab a ruler or something like that to get a line that approximately goes through most of the points. You will never know how difficult that was to actually draw that straight line there freehand. But here we have, I've drawn a line. Notice my line doesn't go through all the points. You'll actually, with this data set, you'll never get a line that goes through all of these data points exactly. But we do notice something about this data. It's that a line almost goes through all of it. In other words, it looks like a line that this data is linearly related. Let me write that definition down. A set of data points is linearly related, or some people say approximately linearly related, if a line can be drawn that is approximately close to all or most of the data points. In our case, we actually have that the line we drew is close to almost all the points. It doesn't actually need to go through any of the points. And if we're going to be exact here, this line might not go through any of the points. It looks like it touches them, but maybe it actually doesn't. Okay, so it does not have to actually touch any of the points. It just has to show the pattern of the points. And it has to be kind of what we call the line of best fit. Now, to do that by hand is near impossible. We rely upon computers to give us the exact best fit or equation of best fit. But for now, we're just eyeballing this business to make some predictions. The beauty of having a line like this is that it allows us to extrapolate or interpolate some information. So let me write down a couple more definitions. It's a very definition heavy section or lecture, but these two definitions are extremely important for data analysis. Extrapolation is the use of a linear model to make predictions outside of the original input set. What does that mean by outside of the original input set? Well, we would use extrapolation to determine, let's say, the percentage of Americans who filed electronically 20 years after 1995. So that's far outside of this set of data. This is our set of input values here that we know for certain we have good values for. That's the inside of our data set, basically. And all this stuff out here is the outside. That's outside of our data range. So when you do extrapolation, you are basically predicting the future or possibly looking back to the past beyond our data. Interpolation, on the other hand, is the use of a linear model to make conclusions or predictions inside of the original data set. And so if we look back again, that would be like if we wanted to know what percent of Americans filed their returns electronically 8 years after 1995. We don't actually have data for that, but we can make an interpolation because that year is within our original set of data. It's not too far. It's pretty constrained. And in fact, it's very easy to see that if you have data that follows a pattern like this, it's very tight in the years that with the data set that you were given. So interpolation is more trustworthy. Extrapolation, on the other hand, in other words, making predictions far outside your data range, is risky, to say the least. And one more thing that I remembered when I was writing this information down, I say the use of a linear model. It doesn't have to be linear in either case. Extrapolation or interpolation just means the use of a model itself to make predictions outside or inside the original data set. Now I'm going to put in a little B star here because I didn't have this in my example set. However, example B said draw a line that comes close to the points in your scattergram. We did. Now I'm going to say find the equation of this line. And here we are now entering into a realm where we have actually done work in the past to find equations of lines. All I have to do is just grab a couple points. And in fact, it doesn't have to be these data points. It could be really anything that you think might exist on this purple line here. And what I'm going to do is I'm going to grab a couple points that don't exist on my data set. In fact, I'm going to use 3. So my input here, let me point an arrow, is 3, but my output, even though on the table is 19, my output on my curve there looks like to be 17. Might even be 18, but I'm just going to take a wild guess and say 17. And here, it's an input of 11, but on my purple line, I know the data says it's 55. My purple line might be at 56. So I'm just using an eyeball technique here. Now that I have 2 points, as we know from previous lectures, you can easily find the slope of this line just using those 2 points. So the slope, let me write m, is equal to, remember, slope is rise over run, or in other words, change in output over change in input. So the output, 56 minus 17, that's a difference in these two y values, or two, I guess they're p values in this situation, 2 output values. And the difference in the corresponding input values is 11 minus 3. So you do a little simple math, you get 39 over 8. Not the best in the world, but that's what we have, right? 39/8. That's the slope. And now I'm just going to go ahead and find out what the equation of this line is by noting that this is supposed to be of the form y equals mx plus b. Y equals mx plus b. That's all lines to me have that form, slope-intercept form. But our output variable is not a y, it's a p. And our input variable is not an x, it's a t. That's fine. I still can do the rest of this. We know the slope here is 39/8. And I have, let's say, I'll select one of my points to plug in for t and p. One of my points here that I just randomly grabbed. I'll grab 3, 17. And you see I end up with an equation where I only have one thing I don't know, and that's b. So let's go ahead and do this. Now this might look pretty bad, but it's real world. That's the way it is. We have 17 is equal to 117, I think, over 8 plus b. And now I'm going to subtract 117 over 8 from both sides. And I'll write 17 as a fraction with the same denominator as this. So it'll be 136 over 8. We're losing 117 over 8. And that's what b is supposed to be. That means b is 19/8. So our equation for this line right here is p, which is our output variable, is equal to the slope, which we said is 39/8, times the input variable, which is t, plus b, which we just calculated to be 19/8. Well, at least they have the same denominator. So, okay, we got a great equation there. The next 3 subparts is really concerning using this equation. So I have the equation written up above. Part C is just saying, estimate when will half of Americans send their returns in electronically. Well, half means 50%. When will 50% of the U.S. return or send in their returns electronically? So I'll write C here. So this tells me that we want our percentage to be 50, and we want to know when that occurs. Well, 39/8 t plus 19/8. My t's look like pluses. Sorry about that. I try to put a little curly Q at the end of my t's. I see an equation here that has fractions. I'm going to multiply both sides by 8. I'll just write this in here to get rid of fractions. I'll multiply everything here by 8. And so this equation becomes 400 is equal to 39t plus 19 I'll subtract 19 from both sides. I think that should give me 381 is equal to 39t. And now I'll divide both sides by 39. When I do this, I get that t is approximately equal to 9.8. I mean, very roughly equal to 9.8. But when you're talking time, hey, that's about 10, right? So it tells me that when t is roughly about 10, half of Americans will send returns electronically. Now we need to interpret this. You just can't leave this as an answer. So you have to say 10 years after 1995. Remember, t is the number of years after 1995. So this basically means that in 1995 plus 10, or in other words 2005, 50% of the U.S. files electronically. Now let's see if that actually makes sense. If we go back to our picture here, a couple of spaces back, remember this is t equals 0 stands for 1995, so t equals 10 stands for 2005. And if you look at 2005, you scroll up here just kind of looking, in other words at t equals 10, it is about 50%, maybe 51, but roughly about 50%. So according to our line, that does make sense. The slope of the equation is 39/8, and the meaning is, well, when converted to just regular old numbers, that's 4.875. And that means 4.875, remember, rise over run, so the rise variable is percent, the run variable is number of years. So 4.875 percent per year means that the number of U.S. or the percentage of U.S. citizens that are filing electronically is increasing by 4.875% per year. Part D, which will write to the right-hand side of Part C here, just says that basically a 1998 law passed that said that the IRS had to motivate 80% of taxpayers to file electronically by 2007. So we're going to use our model here, up here on top, to help us predict whether this goal was reached or not. And to do this, we're going to let t, write this down, let t equal, let's see, 2007 is 12 years after 1995. So we're going to let t equal 12 and find out in that year what percentage of Americans, according to our model, what percentage of Americans filed electronically. So let p equal 39/8 times 12, because that's what t is, plus 19/8. And this is an okay time to use a calculator. It's totally okay. And so I'll type this in. This is 39/8. Actually, I'll say 39 times 12. It's a little bit faster to do it that way. Divided by 8. And then plus 19/8. 60.875. Exactly 60.875. So I'll just go ahead and say this is 60.875%. That's the percentage of the U.S. that was filing, according to our model, filing electronically in 2007. And so therefore, the IRS failed at motivating 80% of taxpayers to send in their returns. So it turns out, according to Part E, that in 2005, they adjusted this law basically to say, listen, we're not going to make the 80% mark. We'll give them until 2011. So let's see if they made it. According to our model. Again, this is all according to our model. Well, 2011 happens to be 16 years after 1995. So we're going to let t equal 16. And I'll put here p is equal to, our model is 39/8 times, and then the 16 that we're entering in, and finally plus 19/8. And again, this type of situation is very easy just to grab a calculator and plug this stuff in. So I'll go ahead and do that. We have 39 times 16/8, which is actually just 2, but whatever, plus 19/8. 80.375. They just barely made it. P is equal to 80.375%. Barely made the 80% mark, so that's good. They made it. They made it there, but they failed in that case. Next group of questions. Yes, I'm a big fan of big groups of questions. I really want to basically squeeze as much as we can out of this problem. So far we've done a little interpolation, we've done a little extrapolation. In fact, the extrapolation, I should have mentioned it here. We did interpolation because we sort of, that t equals 12 is very close. I mean, it sort of is outside our data range, to be honest with you. But I would still, it's only slightly extrapolation. But that t equals 16 is extrapolation. And when we found out the year in which 50% of the U.S. filed electronically, that's interpolation, essentially. But in this problem, or in this group of problems, I'm asking you, what's the meaning of the t-intercept and what's the meaning of the p-intercept? Well, let's go to the graph here. And let me extend this actually out a little bit further so we could see it. Now, in this case, they occur very close to one another, but the p-intercept, here's the p-axis, the vertical axis right here, is the p-axis. I shouldn't be using the bright green. I'll use the red here. That makes it a nice color. That's the p-axis. And this red dot right here is the p-intercept. And the question is, what is the meaning of that intercept? It's a hugely important question. And the answer really is all about knowing what the values of that point are. So the input value for anything on the p-axis is 0, right? That occurs at input of 0. And the output here, according to our model, here's our model right here, when t is 0, our output is 19/8. Okay? Well, that has significance in that it's telling us that 0 years after 1995, so in other words, in 1995, this percent of Americans filed electronically. And 19/8 is roughly 2.4. Okay, so let me go ahead and write that down. The significance of the p-intercept is that in 1995, about 2.4%, or in other words, 19/8% of the U.S. filed electronically. And significant, very, very important that you be able to interpret the value, or the meaning, sorry, of the value of the vertical and the horizontal intercept. Speaking of the horizontal intercept, let's go ahead and interpret the meaning of that right now. The horizontal intercept, and I'll use green for this, it's already highlighted here in green, but the horizontal intercept, well, that's where you hit the t-axis, so that's the t-intercept. And if you write down the values for that point, the output is 0, but the input is some number. And I don't really care, actually, in this example, what that number is. What's important is that the output is 0. Remember, the outputs here are percents of Americans. Well, this means that whatever year that is, because we don't know what year that is, but 0%, or in other words, no Americans filed electronically. So the interpretation of the horizontal intercept, so let me just write F here so that we can see it. F, the meaning of the horizontal or the t-intercept is, it's the year when nobody filed electronically. Now, of course, there's actually a bunch of years where nobody filed electronically. All the years prior to that. But we'll talk about that in a moment. So we have our answer for F, we have our answer for G, and then part H here, it says, is there model breakdown? Model breakdown, I'm not going to write down the definition. It's just basically that, does this model seem silly at certain values? And the answer to that is yes. Yeah, there's definitely some silliness to this model for certain values. Specifically, if you take very negative values like this value, let's pretend that's negative 3. So that's t equals negative 3, which means 3 years prior to 1995, so in other words 1992, we have a negative percentage of Americans. Well, you can't have a negative percentage of anything, so that's stupid. Additionally, if you look on the other side of the graph, this will keep going higher and higher and higher. So at some point, you'll have more than 100% of the U.S. filing electronically. So there's definitely model breakdown. These are things that you have to know when you're working with real data. Now, before I actually continue, I want to bring up something that that would be important for those with graphing calculators. Clear this off. Remember, our graph with the graphing calculator was this. I want you to see that our linear model here is actually pretty good. We have 39 over 8. So all I did was hit y equals to get to the equation part of this. 39 over 8x, because unfortunately it's not going to plug in a t for me, it just calls it x, plus 19 over 8. And if I hit graph, look how close to the data that line is. Very good. I mean, it's an extremely good approximation to the data. The calculator is the only one that could do any better. So I just wanted to show you that so you knew that our line here is actually, in reality, very good. Now, I will do one last brief example. We're actually done with this example because all I can do now is just ask you, well, how many people filed electronically in 2020 or something like that. But these are all things we know how to answer at this point. But this next little bit, just really briefly, and then we'll do a quick example. I want to show you how to use your graphing calculator to find the line of best fit, not just this line that we graphed here. So let me clear this line out. You see the data is still there. You can, using your graphing calculator, find the line of best fit. And this is done using what's called a least squares regression, and you don't need to know that, and you don't even need to know how to do this usually, but let's just pretend that you want to know because it's pretty cool. Now, the first thing I'm going to do, everything that you want to do with statistics, or in other words data points, is done through the stat menu. So if you hit stat, you'll see you have the edit menu where you can edit the list if you want. The rest of this is just silly stuff, so don't worry about that. If you hit to the right one, you see all these things that allow you to calculate, and there are a lot of things you could do here. Like you could calculate the median or the mean of these points, or the average, that type of thing. But what's important is this fourth option here, a linear regression that goes through these points. If you select that fourth option, it will build a linear equation that is the best fit linear equation that goes through, or near to, those points in the form ax plus b. Well, mx plus b really is the way you should think about it. So if I select that, all it does is it returns to me a blinking cursor at the end of that sentence. If you used list 1 and list 2 for your data, which that's what I used, then you could just hit enter. If you didn't use list 1 and list 2, then you would type in the name of the list that you use separated by commas. So for example, L1, comma, L2. But it automatically assumes that you chose L1 and L2, so you don't actually have to type that here. But so I just hit enter, and it says, oh, okay, here's your linear regression. It's 4.5x plus 4.9. Okay, so let me write that down here so that I can see it. So they're telling me that y, even though we're not using the variable y, but let's just use y equals 4.5x plus 4.9. They're saying that's the line of best fit through this set of data points. All right, well, I'll play that game. So let's go ahead and graph this. So I'll just hit y equals so I can get to my graphing menu here, and I'll type in 4.5x plus 4.9 and hit graph. There's the data points, and here's the line of best fit. Now remember, our line was not 4.5x plus 4.9. In fact, it was pretty far off from that. Our line was p equals 39/8 t plus 19/8, which if you calculate this out, let me hit second quit, 39 over 8 is 4.875. So our line of best fit is equal to 4.875, or our line that we said will work nicely. Plus, and then 19 over 8, like I said, is about 2.4. So 2.375. And it's odd that our equation is so far off from their equation, yet when I graph it, I'm just going to go down a step here, and I'm going to type in our values. So I had 4.875, and then the input variable is x, plus 2.375. And I'll hit graph, and there's our line. And look, it's actually still pretty close. I mean, it's not so bad. So even though it looks like it's pretty far off, it's actually not so bad. Looks can be deceiving when you look at this stuff. So anyhow, I just wanted to show you how to find the best fit linear regression equation using your graphing calculator. By the way, if you're following me using your graphing calculator, next thing you'll want to do, if you don't want to do this example ever again, is clear out these equations and go up to plot 1 here. You could actually use your arrow keys to highlight it and just hit enter to turn off your plots. If you do not do that, you are going to hate me, because it will take you forever to figure out how to make your graphs work. Also hit zoom and select number 6, which is standard. The reason why is I'm just getting your window back to the normal operating mode. Okay, there we go. Very last example, very fast example in fact. This is a true story. I weighed actually over 11 pounds at birth, but just to make my life easier for this example, I will say I weighed 11 pounds at birth and 32 pounds at 1 year. And both numbers are approximately correct. How much did I weigh at age 20 if my weight increased at a constant rate? In other words, how much would I have weighed at age 20 if my weight increased at that rate forever and ever and ever? This is also part of a linear model building process. We need 2 points to build an equation, and actually we have 2 points kind of staring at us. At birth, that means at 0 years, I weighed 11 pounds. 1 year later, so at 1 year, I weighed 32 pounds. And look at that, you now have 2 points. And with those 2 points, you could build an equation. And like I said, yes, that's very true. So the slope of this equation will be 32 minus 11, the difference in the y values, over the difference in the corresponding x values. So in other words, that's right, the slope of this is, what is that, 21? Okay. So, 21. I gained 21 pounds per year. By the way, interpreting the slope of this is important. This is pounds per year, right? Because the outputs, the y values, if you will, are pounds. And this is year. So, rise over run would be pounds per year. All right. It's 21 pounds per year. So let's see. Let's build an equation. Y equals mx plus b. And let's figure out what b is here by plugging either of these points in. Usually I take the one with the easier looking points. Let y equal 11. Let x equal 0. And lo and behold, b is just 11. So therefore, y is equal to 21x plus 11. That should make sense, because the fact is, if you read this off, that's my rate of growth in weight, and that's the vertical intercept, the time zero value, or the initial value. That's what I often call that, time zero or initial value. So initially I weighed 11 pounds. Okay. So how much do I weigh at age 20? Well, let's see. Y is equal to 21 times, instead of x here, I'll write 20. And what is that? 420 plus 11, or in other words, 431 pounds. It's not true. Nobody really increases linearly over the years, but there you have it. If my weight did increase linearly, that would be my current weight.